Good afternoon. I'm Jerry Litzel, and this is my course project for Machine Learning Fundamentals. For this project, we're predicting the net hourly electrical energy output, PE, of a combined cycle power plant, a continuous value between 420 and 495 megawatts. This makes it a supervised regression task. The data set includes 9,568 hourly readings with 4 ambient features: temperature, ambient pressure, relative humidity, and exhaust vacuum. Since these are environmental factors influencing turbine performance, I'll start with all 4 as potential features. For algorithms, I consider linear regression as a simple baseline. Had I had a Python environment to do this in, I would have also chosen random forest for its ability to capture nonlinear relationships, and then potentially gradient boosting like XGBoost for higher accuracy. So the first thing I did is randomize the data. I used that with the rand function in Excel in one of the columns and sorted on that column. So after I randomized the data, I split the 9,568 samples into 80% training, or 7,654 samples, and 20% test, 1,914 samples, to evaluate my final model. For model comparison, I use 5-fold cross-validation on the training set to ensure robust performance estimate. I compared 2 models. First, a linear regression model using all 4 features: temperature, ambient pressure, relative humidity, and exhaust vacuum as a baseline. Second, for comparison, a linear regression model using 2 features: temperature and ambient pressure. I trained both models on each fold, predicted PE, and calculated the root mean squared error. The first linear regression outperformed the second linear regression with a lower average root mean square error of 4.4 megawatts versus 4.8. So I selected the first model as my final model. So for evaluation, I chose root mean squared error as my metric because it measures prediction error in megawatts, the unit of the output electricity, and it penalizes larger errors, which is important. It's critical for energy output predictions when you're designing electrical architectures. I also looked at the R-squared value to see how much variance the model explains. After selecting the 4-feature model, I trained it on the full training set, unrandomized data of 7,654 entries, and then tested it, used the remaining 1,914 samples to test. The root mean squared error was about 4.7 megawatts and the R-squared value 0.93, indicating a strong performance in the model. The 4-feature model of 4.7 megawatts means average prediction error is about 4.7 megawatts. That's about 6% of the PE range, suggesting good accuracy for power plant operations. The R-squared of 0.93 indicates the model explains 93% of the variance in PE. So it's capturing most of the environmental effects on energy output. For improvement, we could try different features, different combinations of feature interactions, but this is a solid result for predicting hourly power output. So we're going to stick with the 4-feature model.